right, hello, and thank you for the opportunity to present my work on what might be a slightly different topic, but on the use of machine learning to improve the experimental reconstruction of Fermi surfaces. Fermi surfaces are an important concept in condensed matter physics. They represent a set of points in reciprocal space, or K-space, where the energy of the electron equals the Fermi energy. So the topology of the Fermi surface, it plays a very crucial role in determining a material's properties, such as electrical conductivity, thermal and magnetic properties, and superconductivity. So in essence, it acts as a map of the electronic states that are most relevant to a material's behavior. So being able to accurately reconstruct the Fermi surface is important in order to be able to characterize the properties that a material has, especially like exotic ones like superconductivity. And the image to the right here is the Fermi surface corresponding to copper. Fermi surfaces can be measured using several different methods, but we focused on the angular correlation of electron-positron annihilation radiation. In ACAR, positrons are embedded inside a sample. They annihilate with electrons and emit 2 photons. So the angle of these photons, which are measured by 2 detectors on either side of the sample, encode the electron's momentum before annihilation, and repeating this process produces 2D projections of the 3D electron momentum density, so the momentum along x, y, and z. This is also referred to as a TPMD. And reconstructing this 3D TPMD is an inverse problem, similar to CT or PET scanning in medical imaging. Measurements at multiple angles allow us to reconstruct the full 3D TPMD. From which we can then infer the shape of the Fermi surface in K-space. Conventionally, this is, we use the modified Cormack method, which is adapted for medical imaging and uses crystal symmetry to reconstruct the TPMD with just 5 to 6 projections. It simplifies the 3D reconstruction into a series of 2D problems by decomposing the projections into polar Fourier series. And then you calculate radial density functions, which then tell you how that momentum density is distributed in 3D space. And this allows you to then reconstruct what the original TPMD should look like. Now, experimental measurements are limited by resolution, noise, and smearing. And this is particularly the case with ACAR, which has a very low signal-to-noise ratio. And so acquiring 5 projections at the full counts of 200 million positron annihilation events can take upwards of 3 months. So we then wanted to look at how we could introduce machine learning in order to enhance the reconstructed TPMD. And here you can see, for example, zirconium zinc 2, what the ideal would look like and what an actual experimental reconstruction looks like for the very same sample. So that brings us to DeepCormack, where we figured out a way to use pseudo-real training data, which integrates neural networks at key stages of the modified Cormack method, a reconstruction process. So we have an MLP, which takes the radial density functions and tries to bridge the gap and make them closer to the ideal. And we have a unit, which then takes that reconstructed image and then tries to predict what the remaining residual is to give us like an accurate reconstruction of the TPMD. And then the loss of the model is trained on the actual reconstructed image. And while they performed well on their own, the MLP and UNet, we found that combining them together gave like very exceptionally good results. And with just 50 million counts, we were able to achieve, I have 2 sentences, is that fine? Yeah. Quality equivalent to 200 million counts using just the conventional method. And so this advancement not only reduces the noise and smearing at full counts, but it also shows that we can get very high quality reconstructions at lower counts if we use the DeepCormack method. Thank you.